Okay, welcome back everyone. This is Propositional Logic Part 3. Today we're going to talk about tautologies, contradictions, and contingencies. We're going to talk about equivalence laws, and finally, equivalence proofs. Now last time we talked about compound propositions, which were formed using a combination of connectives. Okay, so compound proposition that's always true is known as a tautology. Now we've got a simple example here. Suppose I had P or not P. And now I've only got the one proposition, so I only need two rows for true and false. Negation P is just going to have the opposite truth values as P. And remember, for a disjunction, only one element of the disjunction needs to be true in order for the entire statement to be true. And that's always going to be the case here. Either P is going to be true or its opposite is going to be true. Therefore, this is true in all cases. Okay, so if we were to translate this into English, right, we might have something like P saying it is raining, negation P meaning it is not raining. Therefore, the final statement would be it's either raining or it's not raining. And that's always true. It's got to be one or the other. Okay. Now, on the other hand, a compound proposition that's always false is known as a contradiction. Okay, so if we took our same atomics of P, right, and now we put this together with a conjunction instead of a disjunction, now we've got P and not P. And if you remember, for a conjunction, both elements need to be simultaneously true in order for the entire statement to be true. And that's never going to be the case when you have something and its opposite. Okay, therefore this is going to be false in all cases. So for our example, this would come out to it's raining and it's not raining. That cannot be simultaneously true, at least not in a single location, right? You can't have something and its opposite coexisting at a single time. Okay, so this is probably the simplest form of a contradiction. Okay, so it's never both raining and not raining. Again, at least in a single location. Now, on the other hand, any other compound proposition is going to be called a contingency because it is contingent or dependent on external circumstances. Okay, so if we took now just our basic P and Q, and we built our truth table with a conjunction, we see that we have some combination of true and falses at the end, right? And this is going to be because this statement depends on the actual state of the world. Its truth value is dependent on those circumstances. So if P was it's raining and Q is it is Tuesday, the full statement comes out to it's raining and it's Tuesday. That's going to be a true or false statement depending on whether or not it's actually raining and it's Tuesday. Okay? So most of the statements that we come across are going to be like this. They're going to be contingencies. Now let's talk about equivalence laws. So last time we showed that two compound propositions were equivalent if their truth values matched in all cases. Okay? Well, through this process, it was able to be determined that a whole bunch of different compound propositions were equivalent. So the first ones we're going to come across are what are called De Morgan's laws. Okay, so De Morgan's laws involve the negation of a conjunction or the negation of a disjunction. And it, in some cases, you can kind of think of this as almost like you're distributing that negation and what that kind of implies. Okay, so the negation of P and Q is equivalent to the negation of P or the negation of Q. So this is like saying, like, in my fridge at home, I don't have both apples and oranges. So this is the same thing as saying that either I don't have apples or I don't have oranges. Right? And a disjunction, remember, is inclusive or, so it could be not apples, not oranges, or both. Number 2, the negation of the disjunction. So not P or Q is equivalent to not P and not Q. So this is like saying, I don't have apples or oranges in my fridge at home. In other words, I do not have apples and I do not have oranges. Okay? So those are De Morgan's laws. Okay, so next we have what are called identity laws. So rule number 5 says P conjunction and a true statement, P and a true statement, is equivalent to just P by itself. So if you remember, a conjunction can only be true when both elements are true simultaneously. Okay, so if we know that this is overall a true statement, and you know that the other part is true, well then your first element also has to be true. For rule number 6, P or a false statement can be reduced to P as well. Okay, so for a disjunction, at least one element needs to be true in order for the statement to be true. So if this entire statement is true, but that element is false, you've determined that this element is false, maybe it's a contradiction or something like that, well then the first part has to be true. So you can simplify that to the first part. Okay. Next we've got domination laws. Okay, so this is saying that one part of this conjunction or disjunction dominates the entire statement. So they're very similar to identity laws, but they're kind of going the other way. So if we had a disjunction now, and we know that just one element of this disjunction is true, well then the entire disjunction is true. If you have a conjunction, and you know that a single element in that conjunction is false, the entire conjunction is false. Okay, and that's just operating off the same rules that we had for conjunction and disjunction to begin with. Okay, then we've got idempotent laws. Now this is just saying something like if you have a redundancy, if you have something like P or P, well you can just simplify this to P. Same with P and P, you can simplify this to P. And this sort of redundancy might come up when you're working in an equivalence proof and you're reordering or substituting and things like that. So when different elements of the statement come together, you might end up with these sort of redundancies, and you can reduce them like this. Okay. For number 11, we've got the double negation law, which is not really any different than saying just, the negative of a negative is a positive, right? We've got that property in math. So the negation of a negation is equivalent to the original statement. Okay, then we've got the negation laws. And these are actually these are our same tautology and contradictions from before, our examples from before. So if you have something like P or not P, this is going to be a true statement by default. That was literally our example for a tautology. We've exhausted all possibilities there. It's got to be one or the other. For number 13, P and not P, this is necessarily false. This has to be a contradiction. We cannot have both something and its opposite simultaneously. Okay, so if you get either of these in some sort of equivalence proof, you can reduce the entire thing to a true or a false. That you can, then use with one of these laws potentially to go further. Okay. Then we've got the distributive laws, 14 and 15. This is kind of telling you how we can, if we've got a disjunction and one element of that disjunction is a conjunction in its own right, how can we go ahead and kind of distribute this out and expand the statement? So P or Q and R is the same thing as saying P or Q individually and P or R. 15 is saying P and Q or R is the same thing as P and Q or P and R. Okay. Next, we've got the commutative laws and the absorption laws. So the commutative laws are really straightforward. They're just telling us that we can reorder something like P or Q into Q or P. P and Q is the same thing as Q and P. Okay, this is no different than saying something like 2 plus 3 is equal to 3 plus 2. They're the same thing. Okay, this just might be for the sake of convenience, so we can group things together and further simplify them. Then we've got the absorption laws. So this is something like, for 18, we've got P or P and Q. So because P is showing up twice here, this will leave us with something like P or P. And we can simplify that to P. Same thing with this, right? So we've got P and P or Q. If we go ahead and we use one of our prior laws, like the discrete law, right, we're going to end up with the statement of P and P, which we can simplify to P. Okay, next we've got our associative laws, and this is just allowing us to regroup our variables or propositions when we have the same symbol across the board. So if you have two disjunctions, it doesn't matter if you do P or Q first, or R or P, and then Q or R in parentheses. Same thing holds for the conjunction. This just, when we have the same symbol in both cases, we can group either the first two terms together or the second two terms together, and this would hold for any number of terms, okay, as long as they're all the same symbol. And finally, we've got the conditional disjunction law. So this is saying if P then Q is equivalent to the negation of P or Q. Okay, so this is allowing us to rewrite the conditional statement as a disjunction. And for this one, let's see why this works. Okay, so we've got a truth table here. We set up our P with 2 trues, 2 falses. Q is alternating. Negation P is going to be 2 falses and 2 trues. The conditional, if you remember, so we've got true and true is true. Antecedent true, consequent false is false. And then we had our 2 vacuous truth cases. And actually, this is going to explain why these vacuous truth assignments were made. It's because it allows us to have this equivalence. Okay, so negation of P or Q is true. When both are false, the disjunction is false. In this case, both elements are true, so the entire statement should be true. In this case, one statement is true, or one element is true, so the entire statement is true. And this allows us to equate these two and create this equivalence. Okay, so this allows us to kind of bring our system of propositional logic full circle and make really useful equivalences like this. Okay, so next, let's talk about equivalence proofs. So let's see how we can use our equivalence laws to show the equivalence between two compound propositions without having to make a truth table and show that those values are all the same. Okay, so for our first example here, show that if P, then negation Q, implies if negation P, then negation Q, show that all of this is equivalent to just P or Q. In other words, we're kind of taking this really complicated expression and simplifying it down to its kind of basic element. All right. So step 1, we can take that main operator conditional, we can apply the conditional disjunction law and turn that into a negation of the antecedent and turn that main operator into a disjunction. Okay. For step 2, we can do exactly the same thing inside each set of parentheses. So we can turn those individual conditionals again, into a negation of the antecedent and a disjunction. Negation of the antecedent and a disjunction. Okay. Now in the first set of parentheses, we're left with a negation outside of a disjunction. We can go ahead and we can kind of distribute that, right? Using our De Morgan's laws. That will give us a double negation on P. The disjunction is going to turn to a conjunction. Double negation on Q. Then we can go ahead and we can actually simplify those double negations, right? Using law 11, double negation law. Double negation P is just going to become P. Double negation Q is just going to become Q. And same for that second set of parentheses. Double negation P just becomes P. And now we're actually starting to see that element that we were looking for, hoping to simplify to. Now from here, in step 5, we can kind of consider this entire first set of parentheses as just some singular statement A. And this now is of the form A or P or Q. And if you remember, the associative law, as long as all of those operators are the same, allows us to group together or associate whichever two at a time that we want. So we can go ahead, we can take this set of parentheses from here and apply it to that first part. Okay, and that allows us to essentially group this P with this P and this Q. Okay, in its own set of parentheses. Now here, we have some redundancy, right? So the absorption law allows us to take that first set of parentheses, this is law number 18, and simplify it to just a P. And we've got exactly what we were looking for, P disjunction Q. Okay. That was our first example. For our second example, show that the negation of this complicated set of brackets, show that this whole thing is a contradiction. Okay. So let's take it kind of piece by piece and see what we have inside. So we've got our main operator is a conditional. We've got one set of parentheses here for the antecedent, one set of parentheses here for the consequent. Within the antecedent, we have a conjunction, and each of those conjuncts, each of those elements, is itself a disjunction. Okay, and the consequent of this overarching conditional is also disjunction. Okay, so we want to show that this is a contradiction. So hopefully we can get to something like P and not P, or two false elements, something of this nature. All right, we're hoping to show that this entire statement is false. So let's start off the same way. Let's use our conditional disjunction law. We'll turn that main conditional into a negation of the antecedent and a disjunction here. Okay, so note, we're going to leave that negation outside the brackets for now. Technically, this is the outermost operator, but we're going to leave that out there for now because we don't have anything that will work with a negation of the conditional yet. But once we've done this, once we've made this into a disjunction, now we do have something that operates with a negation and a disjunction, right? We know how to further simplify this. So now we can go ahead, we can kind of distribute this negation. You're going to get double negation here for the first element. Your disjunction is going to become a conjunction, and your second element is also going to get a negation by De Morgan's law. Okay. We can go ahead, we can simplify the double negation up front. Okay, take away those extra symbols that we don't need. So that first element is entirely just by itself. We have a conjunction, negation of our second element. Now for our second element, again we can use De Morgan's law. We have a negation of a disjunction. So this is going to become negation Q and negation R. Now, for this next part, it'll just be a lot easier if we turn all of these elements and kind of just rewrite them as A, B, C, and D. It'll be a lot easier to see what's kind of going on here. So we're going to use a bunch of associativity and commutativity laws, and we're going to try to regroup these in a way that will be beneficial. Okay. So first of all, we see that we have conjunctions between everything. So that's really helpful. So for associativity and commutativity, we can just start reordering everything. Okay, so first we put this C over here in a parentheses with A and B. We can, instead of grouping A and B together, we can first group B and C together. We can swap the order of them. So this is going to become C and B. And then we can group that C with A. And we can do the same thing. We can group this B with this D. Okay, so why would we want to do this? Why would we group A and C together and B and D together? So if you see, first of all, B has an R. D has a negation R. If we can put those two together, we might be able to construct a contradiction. Okay, same here. With A, we have a Q. With C, we have a negation Q. If we can get those two together, we can also potentially construct a contradiction, right? Our point here is to try to prove that this entire statement is false. So we want to try to put those contradictory elements together. Okay, so for our next step, we can go ahead and we can use a distributive law. Okay, so now that we've got this, we can go ahead, we can put this negation Q with each of these elements, P and Q. Same thing here. We can put this negation R with the negation P and R. Okay? So this conjunction is going to apply individually to the inner parentheses, and that disjunction is going to come outside. So we're left with P and negation Q, or Q and negation Q. And this is exactly what we were hoping to get. And the second set of parentheses do the same thing. This conjunction is going to go inside on both parentheses. That disjunction is going to come outside. This negation R is going to get paired with each of these elements. So you've got negation P, negation R, R, and negation R. And again, this is exactly what we wanted. Okay. So now I've got those contradictory elements highlighted. Because these are contradictions, by negation law, I can just substitute a false in there. Okay, so now I know both of these elements for a fact are false. Now, when you've got a disjunction, and one element is false in disjunction, by the identity law, it tells you that, well, the first one, if there's any hope of this being a true statement, the first one has to be the truth, right? So we can go ahead and we can reduce this, cut out that false element in both disjunctions. And that leaves us with P and not Q, and not P and not R. Okay, let's go ahead and use our associativity and commutativity again. So this negation P is going to come over here into the first set of parentheses with that P. This negation Q is going to come over into the second set of parentheses with that negation R. And now we've got another contradiction, P and not P. So we can go ahead and we can assign that a false value. Now, if you have a false statement or false element in a conjunction, it doesn't even matter what the rest of the conjunction is, because the only way a conjunction can be true is if both elements are true. Therefore, by domination law, right, so the truth value of this conjunction is dominated by this one false element, the entire statement has to be false. In other words, this statement is necessarily false and a contradiction. Okay? So I know that was a complicated example. Hopefully that made sense, but the the way to go about these is to try to do as many examples as possible, and hopefully they become a little bit more intuitive. All right, so this was Propositional Logic Part 3. If you found this lecture helpful, please give it a like and subscribe so you don't miss the next one.